This video note is a brief description of the derivation of equation 13.6.11 in the textbook. I consider equation 13.6.11 to be very important, and it should probably get its own special box, but since the author has not given it its own special box, I'm going to dedicate an entire video note to this short derivation of equation 13.6.11. So the point is that we have some constraint relation f between two variables x and y, and we would like to use this constraint relation to generate an implicit function y of x. So I'm treating x as an independent variable, and I want to see how y varies as a function of x by demanding that this constraint relation remain verified. And then that creates a function that I'll call y tilde that the author has just called y of x. I think it's a little bit confusing because it's not clear when y is being treated as a function and when y is being treated as an independent variable. So I will always call my functions y. I'll put a little tilde on top to remind the reader that this is in fact a function in its own right. Okay, and so the point of equation 10 and 11 is that if I think about the derivative, so if now I treat f as a function of a single variable, so f of x, so now I'm composing here. So that's my function of two variables, f of x, and then I'm going to evaluate y. I'm going to set that equal to my function, y tilde, evaluated at the given x. Okay, so this object here is really a function of two variables. This object here is a function of only one variable. Okay, so I don't need to talk about total derivatives. I don't need to talk about partial derivatives. I can take the total derivative of f of x with respect to x, okay, and then, just like before, I can use the chain rule. So this is the partial of f with respect to x plus the partial of f with respect to y, and then I have the derivative of my implicit function with respect to x. So this is simply the chain rule, but since f is always 0, at any given x, well, its derivative certainly has to be 0 if it itself is always 0, so this has to be equal to 0. And so that immediately gives us a relationship between the derivative of our implicit function, y tilde of x, and our partial derivatives of f. So this would be negative f, the x partial divided by the y partial. And this expression immediately tells us that if the y partial derivative is equal to 0, there's going to be a problem because my curve y tilde as a function of x will come to a vertical tangent, at which point it will could potentially cease to be defined afterwards. Okay, so I will give this a special rainbow colored box. And I wish the authors had made that a special color, but this is equation 13.6.11.